Good morning, everyone. My name is Miriam Bastante. I'm a physicist, and I work in quantum computing team in Eviden Iberia. In this talk, I will discuss 3 important points. A brief introduction of quantum computing, Eviden quantum strategy, and our emulator Qaptiva, and finally, a proposal we have developed in Qaptiva. In quantum computing, it's currently not only being considered in various companies, academic articles, or media from a theoretical perspective, but it's also a reality. So applications are in fields such as pharmaceuticals or optimization. And this is the McKinsey sentence that summarizes the importance of quantum computing. We may ask, why noise is important in quantum computers? We are currently in the NISQ era, and the existence of noise in quantum computers is one of the challenges we must overcome. When run an algorithm on a quantum computer, the presence of noise limits the potential that quantum computing can achieve. Some of the main problems are scalability and fidelity of the quantum systems. The physical qubits with a quantum computing are not the same as logical qubits, where quantum operations are performed. In other words, we need several physical qubits to create a one logical qubit tolerant to errors. To illustrate how noise can affect the quantum computers, I will show the following example. Given a deterministic circuit, meaning that a circuit with an output or another depending the inputs it receives. If execute it in a real computer, we may obtain a correct state, like this picture. We obtain the 1001, or in the case we could obtain other state, in this case 0001, that it's incorrect. Therefore, noise can lead to errors in obtaining the final state of the circuit. This state is correct, and this is not correct. This is because the noise. Many of you may ask, why use an emulator and not a quantum computer? The truth is, I consider that use an emulator, it's a complement. It's not substituting a quantum computer. However, the main advantages it offers a quantum computer are following. The availability, it runs locally, and its availability is total, no waiting queues. The emulators usually offer a greater scalability. The costs it's lower than quantum computer, and the quantum emulators allow reproducibility of the results using the same seed, and finally we obtain intermediates and final measures can be visualized. Now I will discuss about the Eviden strategy. The name Qaptiva, comes from a Latin word, captivare, that meaning an irresistible attraction because of their extraordinary qualities. Our strategy until now consider of presenting a shared memory appliance that hardware and software in quantum emulator called Qaptiva, which was designed for research centers, universities, industries just starting in quantum computing. Now we offer a total emulation environment that includes emulation system, Qaptiva, and a differential strategy. Our slogan is make the impossible possible. This is Qaptiva Access. Qaptiva Access is a solution that enables the integration of HPC systems, Qaptiva series 8800 and MyQLM, that is a freeware of Eviden, and QPUs to which have access. All of this is managed for Slurm. The Qaptiva emulators allows simulations of three types of computing: digital, analog, and annealing. From a hardware perspective, you advocate for an universal, agnostic, interoperable quantum language that allows simulation with and without noise, a powerful emulation that allows the inclusion of GPUs, accelerators up to 12, the speed up, a scalable and modular appliance. The scalability and flexibility in our device can be expanded over time with new sockets without losing the initial investment. As shown in this graph, you can start with a Qaptiva 802 with 16 qubits, and research a Qaptiva 816 with 41 qubits. For a software perspective, Qaptiva has three environments: programming, optimization, and emulation. In programming, the important parts are combinatorial optimization and interoperability with other frameworks like Qiskit, Rigetti, or Cirq. In the part of optimization, we have PEO, Circuit Optimizer, and NISQ that optimize the topology. And finally, the emulation, it's with noise and without noise. This strategy relies in two axes: services and products. In the case of services, we have a consulting team and a support of using QPUs through agreements with third parties, and quantum computing as a service, which provides a cloud-based emulation services. In the case of products, we have hardware, Qaptiva series, Qaptiva Access, and software licenses for HPC clients or third parties libraries. And finally, we have the freeware MyQLM. And finally, I talk about our proposal in Qaptiva. Firstly, I talk about noise modeling. In a basic circuit like that, we show the different sources of noise it presents. At the qubit level, we have gate error in single qubits and 2 qubits gates. The spam errors includes state preparation and measurements. And finally, idle noise, it's focused on environmental circuits, the conditions, sorry. These noise sources can be grouped for various of noise models. In our case, we have 3. The polarizing channel noise model that involves gate error and spam error, Lindblad model and thermal relaxation model that focus on idle noise. These 2 noise, Lindblad and thermal relaxation model, are a similar noise modeling, which have chosen Lindblad model for Qaptiva and thermal relaxation model for Qiskit in our comparison. The methodology we follow, it's based on this workflow. Firstly, I send a quantum circuit to a QPU and transpile, converting the circuit gates into the native gates of the of these QPU gates, native gates. Next, calibration data is obtained for the QPU that we use at that moment, and corresponding topology was created with our plugin NISQ. Next, use a noise modeling, hardware noise model, and finally obtain the results of this circuit. The metrics we use are fidelity and time of execution. We have carried out this test with IBM Perth with this topology, I-shape topology. The colors represent lighter colors represents maximum higher error, and darker colors represents lower error. And we use NISQ that have these methods, and we choose Sabre and initial mapping with these gates that this is for these methods includes swap gates, and we choose the one of the lowest introduced swap gates. We can observe that PBN, this method, lacks of number of gates. This is because it doesn't allow the custom gates we use. We have used custom gates in Qaptiva because Qaptiva doesn't have SX gates predefined. This slide shows a circuit adder with discomposed gates into a native gate of IBM Perth backend. Initially observed by default, the emulator assigns the same time to each gate, and modeling, and we apply the hardware model, and corresponding time is applied based on the values obtained from the calibration data for the backend. It can be observed that C0 and measurement gates with longest application times. This is the circuits we have chosen for this experiment. We have tried to choose circuits with different characteristics or size. The Grover and eSwap it's have a small size. Cat state another, we consider it's a medium size, and error correction with a large size. We have compared the modeling in Qaptiva with Qiskit, with air simulator of Qiskit, which allows the noise simulation up to 30 qubits, use a noise models model which contains functions to create a noise modeling like Qaptiva. In particular, we use a combination of the polarizing error and thermal relaxation error that it's equivalent to Qaptiva with Lindblad model. And we compare these Qaptiva and Qiskit under similar conditions. This graph shows the differences between backend and emulators. Backend represents IBM Perth in blue. I don't know if you see, in blue. Qaptiva in orange, and Qiskit in purple. As seen in this table, the noise modeling is quite accurate as the absolute differences. The absolute differences in fidelity quantum emulators with backend are quite small, like that. Small. The difference in Qaptiva are smaller than Qiskit, especially in the case of cat state, with an order of magnitude lower compared to those in Qiskit. It's also been observed that circuits with a large number of qubits and depth have a smaller fidelities because they're more affected by noise. And finally, in this table, we have a comparison research between Qiskit and Qaptiva. Both small and medium have great fidelity values. Light is slightly higher in Qaptiva. However, in large circuits, Qaptiva modeling fits better. However, there is a greater differences compared to the backend use in the circuit than the others, large, like the small and medium sizes. And finally, I talk about the future lines to complement in this study, performing tests with a higher number of qubits or depths, analyze the impact of noise in different topologies, and finally, Qaptiva is an agnostic emulators. And it allows to implement this noise model on different quantum technologies like photonic, ion traps, neutral atoms, and observe their behavior. Thank you.
Thank you, Miriam. Any question from the audience? Okay.
So how do you simulate the evolution of quantum states? Do you do like a vector state simulation, or do you do like tensor networks?
Vector state simulation, no tensor networks.
Any other question from the audience? So when I was seeing your presentation, I get some question in my mind, but finally, I have some of them. One of them is when you were explaining the way that you make the model for noise correction. You say that you are taking information from the QPU.
Yeah.
And then at the end, you were saying that the next action is using not only one technology of qubit, using another one. Do you expect any change in the model, or?
We expect that we need to obtain the calibration data of the ion traps. It's more difficult than superconducting, and we try to talk about other companies to give us the calibration data for modeling the noise modeling and hardware, and use the QPU calibration data of ion traps.
So did they have just a big model with all technology, or have separated model according to the user needs?
This methodology is for all
The different
QPU
okay.
or QPUs.
Okay.
Not only superconducting, but we try in superconducting because IBM have.
Yeah. And the other question is related to fidelities.
Yeah.
Because I know that what is a fidelity, what is talking about, but I don't know what is the limit that you say I can trust this this gate or not. I cannot trust it.
I trust no limits, but the more fidelities in IBM pairs we obtain are about 0.92, more or less.
So that means that it fails the 8% of the times.
Yeah.
Well, they are improving a little bit. Any other question from the audience? So if not, let's thanks again, Miriam.
Thank you.